The main focus of today's lecture is Hilbert basis theorem, which says that if R is any Noetherian ring, then the ring of polynomials with coefficients in R is also Noetherian. As a reminder, we defined a Noetherian ring as a ring all of whose ideals are finitely generated. A historical remark. David Hilbert was one of the most famous mathematicians of the turn of the century. So he was born in 1862 and died in 1943. And he worked in many areas. Among those are commutative algebra, algebraic number theory, foundations of geometry, and foundations of mathematics. In particular, proof theory. And he's famous for creating the list of open problems in mathematics, which proved to be very influential. It is called Hilbert's problems. And there were 23 of them, of which 8 are solved. Some of them are partially solved, and one of the most famous unsolved problems from his list is the Riemann hypothesis. And it is a conjecture about zeros of the so-called zeta function. Before I go to the proof of this theorem, I want to formulate some corollaries of it. So first, proposition: if R is Noetherian and I is an ideal in R, then R mod I is also Noetherian. And for the proof, I pick any ideal J in R mod I, and if Q is the quotient morphism, then I can take the preimage of J bar, and I call it J in R, and this is an ideal in R, and R is Noetherian. Therefore, J is finitely generated. Let's say by elements R1 through Rn. And then it follows that J bar is also generated by the elements, by equivalence classes presented by these elements R1 through Rn. And it proves that J bar is finitely generated. And so a corollary of the Hilbert basis theorem combined with this proposition is that if R is Noetherian, then first a ring in any finite number of variables is Noetherian, because we know that since R is Noetherian, then R adjoint x1 is Noetherian, and then we adjoint x2 to a Noetherian R adjoint x1, etc. So the proof is using this theorem by induction. And the ring of polynomials mod out by certain relations. So we take polynomial functions, f1 through fm, and generate an ideal by them. So because of this proposition and the first part, this ring is also Noetherian. So basically you start with any field or PID, and then you adjoin any number of variables, and possibly mod out by some equations, and you still remain in the realm of Noetherian rings due to this theorem. Let's now turn to the proof of Hilbert basis theorem. So we have a Noetherian ring R, and we want to prove that R adjoint X is Noetherian, and to this end we pick some ideal I in R adjoint X. And what we want to show is that I is finitely generated as an ideal of R adjoint X. So the first step is we define the ideal of leading coefficients. So I take J to be a certain subset of Rn in R for every polynomial Rn xn plus etc. plus R1x plus R0 that is taken from I with the zero element. So it is a subset of R, and the claim is that J is an ideal of R, and it is called the ideal of leading coefficients. So the proof of claim is pretty formal, so I'm going to prove it on this side. So the more tedious part is to show that a sum of two elements of J is still in J. So let's take R and S in J. So there exist polynomials f, g in R adjoint X, such that R and S are their leading coefficients, such that f of x is equal to R x to the n plus R n minus 1 x n minus 1 plus etc. So R is the leading coefficient of this polynomial, and it is in I. And similarly, g of x is s x to the n plus s m minus 1 x m minus 1 plus etc. till s0, and it is also a polynomial in I. And then, without loss of generality, assume that m is not smaller than m. And in this case, I can consider the sum f of x plus x to the power n minus m times g of x. And because f and g are in the ideal I is closed under multiplication by all polynomials, and it is also closed under addition, so this sum is still in I, and its leading coefficient is exactly the sum of R and S. And the easier part is that if R is in J, then for any element A in R, AR is still in J, and this is because we can multiply any polynomial by A, and it multiplies its leading coefficient by A. So this is the proof of the claim. And now J is an ideal in R, and R is Noetherian by assumption. So J is finitely generated as an ideal of R. So let's say that J is equal to, so is generated by R1 dot Rn. And for each Ri, pick Fi, a polynomial in X, such that Ri is the leading coefficient of Fi. So we can multiply each polynomial by a power of x. So again, without loss of generality, we can assume that degrees of all of these polynomials are the same. So degree of f1 is equal to degree of f2, etc. through fn. And let's say that the degree is d. And now I can outline the rest of the proof. So we can view R adjoint X as an R module, and as such it is a free module, isomorphic as R modules. It is a free module on generated by the element 1, the constant polynomial 1, x squared, etc. So let me write here plus rx to the power d minus 1 plus rx to the power d, etc. And in the rest of the proof, I will pick an element. I will start with a polynomial of degree smaller than d, and I will show that this polynomial can be generated by fi's and some finite number of generators of degree smaller than d. And then I will inductively reduce the case of polynomials of greater degree to the case of polynomials of degree at most d minus 1. So note that this part, R1 plus etc. through Rx d minus 1, it is a It is a finitely generated R module. So I denote this module by M. So M freely generated by 1, x, etc., and all monomials of degree at most d minus 1. It is a finitely generated R module. And I, the ideal in Rx, intersected with M, is a submodule, is an R submodule. And because R is Noetherian by assumption, we proved last time that it means that every submodule of a finitely generated module is itself finitely generated. So I plus M is finitely generated as an R module. And let's say it is generated by elements G1 through Gm. So Gi's are polynomials of degree at most d minus 1. But this module is not necessarily free, and we don't care if it is free or not. And now I claim that the ideal I in R adjoint X is generated by Fi's and Ji's. It's generated by the set F1 through Fn, G1 through Gm. Okay, so for this, I pick any element H, a polynomial in I, and I want to show that there is a linear combination of Fi's and Gi's that is equal to H. And this linear combination is taken with coefficients in R adjoint X. Okay, so case 1 is when the degree of H is smaller than D. Then H is in fact lives inside M. Then H lives inside M. And H was in I, so it lives in M intersected with I. And so H is generated by Fi's with coefficients in R. So H belongs to the ideal generated by F1, G1 Gm, and so we can generate H with this finite set. case 2 is when the degree of h is at least d. Then we want to reduce it to case 1. So how do I do it? So let's say that the degree of h is equal to k. Then I can write h as ak xk plus dot a1x plus a0. And ak is the leading coefficient of h, and therefore it lives in the ideal of leading coefficients. And therefore ak can be written as a linear combination of ri's. So ak is equal to c1 r1 plus etc. cn rn. And if I subtract the corresponding linear combination of fi's from h, then I will get a polynomial of smaller degree. So the degree of h minus the sum over I of ci fi is strictly smaller than the degree of h, because we subtract from the leading coefficient ak the linear combination of ci's times the leading coefficient of fi, and I should also multiply this by the necessary power of x. So I multiply it by x to the power d to the power k minus d. And so we get the following picture. If the polynomial h has degree smaller than d, then it lives in this pink R module, and it is generated by fi's. If the polynomial h has degree, let's say d, then we can subtract from h a linear combination of fi's to get it to a polynomial in this smaller, to get a polynomial of smaller degree, and then it will be generated by gi's, etc. by induction. So if we take a polynomial of degree d plus 1, we reduce it to the case of d. And so by induction we conclude that every polynomial h in I is generated by this finite set with coefficients in R adjoint x. And this concludes the proof.